I'm Mr. Black, and tonight we're going to try to apply Newton's laws of motion. And we're going to find a few quick steps. One is make sure you always read the problem carefully. And when you're done, reread it. You want to identify your target. A huge part of what we'll be doing here is just taking ideas and trying to solve problems. Make sure you imagine the situation in your head and then draw it. You can do stick figures, you can draw anything, something that helps you to visualize it. Once you've done that, you want to make sure you make a free body diagram. So I'm going to do a sample problem, actually two problems tonight, and you'll see that it ends up always at some point with a free body diagram. We can then use that free body diagram to start thinking about, do we have a net force? What would be the net force? And that's really going to help set up the problem. So finally you can simply use Newton's second law of motion. Newton's second law of motion is F net equals m times a, or acceleration equals the net force on the object divided by the inertia or the mass of the object. So let's go ahead and get started tonight. It's easiest to illustrate this with a specific problem. I'm going to do question 113, which could be found on page 185 of your textbooks, and that reads about a parachutist, and it's a 42.0 kilogram parachutist moving straight downward with a speed of 3.85 meters per second. A, if the parachutist comes to rest with a constant acceleration over a distance of 0.750 meters, what force does the ground exert on her? And B, if she came to rest over a shorter distance, is the force exerted by the ground greater, the same, or less? So let's reread that problem as you should do in any case where you're struggling over a problem. And I see immediately they're giving me 42.0 kilograms. I hope you recognize that as being a mass. We know the mass of the parachutist. We know that the parachutist is right now suspended from the parachute going down. And they give us a velocity, a speed actually. So there's no direction yet. They just say 3.85 meters per second. We of course know that would be down. We also know that the parachutist comes to rest. So that 3.85 must be my initial. Once they come to rest, that's the final. That'd be 0 meters per second. And we know this happens over a distance of 0.75 meters, but I have to use displacement in my kinematics equations, so I want to go ahead and set up a coordinate system. I decided to make plus down, and this will illustrate how you really can come up with your own coordinate system, but you have to be consistent. So keep in mind what I'm doing here. And what's my target? The actual question is force. I want to find what is the force exerted by the ground. So I need to find F ground. So I'm imagining the situation in my head and I want to draw it. And I've kind of begun that drawing process, but let's focus on the part that really matters, the landing. So we have our parachutist, and he's coming down, and he's been, of course, gravity taking him down, but he now hits the ground, and that's a force upward. So let's do a free body diagram, as we should always do. I'm going to start with him when he was still in the air. If he was going at 3.85 meters per second as a constant velocity, then there's no acceleration. So, of course, the parachutist has weight, the force of gravity on his 42 kilograms, but the air resistance vector should be exactly the same. The forces should be balanced. And that would be the same case at first when he hits the ground, but now we would have an additional force. We'd have the force of the ground. So I throw that in my free body diagram. And I want to use that free body diagram to try to find what would be my net force. And the one that matters here, there's three forces, but two of them cancel each other out if I do tail to tip. The only one that's not canceled out is the F ground. So that is my net force. It's the only force that remains. An upward force exerted from the ground. Well, that's good news, because that's what Newton's second law is about. And of the two versions, this is the one I would want. F net equals m times a. That F net, that's going to be the ground force, the force exerted by the ground. And I just need to know the mass, which I know, and oh no, the acceleration, which I don't know. I can't use that 0 because we don't care about it in the air. We want to know the landing. And we do have a change of velocity upon the landing. But we can still use our kinematics equations. Those are not going anywhere. We can use them to get A, because we know a VI, we know a VF, we know a displacement, and we're trying to solve for A. The only equation that deals with those four variables is the fourth kinematics equation. So I can manipulate that, subtract VI squared from both sides, divide both sides by 2 times the displacement to isolate the acceleration. And now I've got variables I can plug in and I can solve this. In fact, I can even simplify it because I know my VF, the final velocity, is 0 meters per second. So why keep that in the equation? Let's simplify it to minus VI squared, the initial velocity squared, divided by 2 times displacement, and that's going to give me my acceleration. So I can plug in the variables I know. I know my VI is 3.85 meters per second. I'm keeping that positive because I already set down as being positive in my strange world. And I'm going to divide by 2 times 0.750 meters, which I can keep positive as well. And so once of course that's my displacement. And then once I go ahead and find the square root of 3.85, it is 14.8225 meters per second squared, but I need the negative version of that because it's minus VI squared. And then 2 times 0.750 meters gives me 1.50 meters. Now a little dimensional analysis here. That would get rid of one of the meters, the one on top, and I'm left with meters per second squared. Am I happy? I might not sound like it, but I'm extremely happy right now because that's what I want for acceleration. So I do the last step in the calculator and I get 9.816, repeating 6s, meters per second squared. That is based only on, truthfully, 3 significant figures, but I'm going to not pre-round. And then I can multiply the mass, 42.0 kilograms, which is 3 sig figs, times that 9.8816 repeating meters per second squared of 3 sig figs. And upon doing that, I get an answer of negative 415.03 kilogram meter per second squared. And that's awesome, except remember it's supposed to be 3 sig figs. So my real F net is minus 415. Instead of kilogram meters per second squared, that is a derived unit, or leads to the derived unit called the Newton. So that's just called a Newton. It's so much easier. The big capital N. And what about that minus? Well, remember my coordinate system here. Minus in my coordinate system is up. It's up. So therefore, that 450 newtons is directed upwards. And so there's my final answer. F net equals 450 newtons. And that F net is the force exerted by the ground. That's how it works. And that is the correct answer. During skydiving, Timmy Tork is falling at a terminal velocity of 53.5 meters per second. Once he opens his chute, the force of air resistance shoots up to 1,325 newtons. The force of gravity on Timmy Tork is 824 newtons. Timmy has a mass of 84.0 kilograms. What is Timmy Tork's acceleration the moment his chute is deployed? Terminal velocity 53.5 meters per second. That's a velocity, not acceleration. Force of air resistance up 1,325 newtons, upwards. Force of gravity 824 newtons, that's always downward, and my target is acceleration. Acceleration, solving for acceleration. Okay, let's imagine it. So the chute opens, boom, and there it is. It's deployed, it's out. Okay, seeing it. Let me see a side view. I get it now. So the chute's there, catches all that air, catches a lot of air resistance. So we got two forces going on. Got it. Oh, look, Mom! He's making a coordinate system! Up! Make it plus up! Yeah! Plus is up! Oh, I do hope he does a tail to tip. There it is! Tail to tip! Oh, look, Sonny boy, he did it right. Hold on a god darn minute there. You saying he's allowed just to do that? He can just go ahead and throw those things away? Yes, sir, that's how it works. That's called vector reduction. If you added them up, you can go ahead and do that. Now you use Newton's law of second law of motion to solve for your target. Go!